Welcome to Instrulogic YouTube channel.
In this video, we'll learn about Programmable Logic Controllers, or PLCs. These devices are the backbone of industrial automation. They help control machines and processes in real time, replacing old relay-based systems with smart, programmable logic. By the end of this course, you'll understand how PLCs work, their architecture, and how they are used in industries. Before we dive in, let's look at what this course covers. We'll start with an introduction to PLC and why automation is important in industries. Then we'll learn what a PLC is, its history, and basic architecture. We'll go through how it works, different types, hardware components, and programming languages. Next, we'll cover communication and networking, compare PLC with DCS and local control panels, and see major PLC manufacturers. We'll also explore real-world applications, an example of tank-level control, advantages of PLC, and finally, troubleshooting and maintenance. At the end, we'll summarize.
Let's start with the basic. PLC stands for Programmable Logic Controller.
It's basically a small digital computer designed to control machines and processes in real time. Instead of using old relay-based systems, PLCs use programmable logic, which makes them flexible and easy to modify. They are widely used in industries to automate tasks, improve efficiency, and reduce errors. Why do industries need automation? The main reason is to improve productivity and accuracy. Automation reduces human error and makes processes more reliable. It also increases safety for workers and ensures better monitoring and data logging. Another big advantage is lower maintenance costs because automated systems are more consistent and easier to manage. In short, automation helps industries run faster, safer, and more efficiently. So, what exactly is a PLC?
A Programmable Logic Controller is an industrial digital controller.
It continuously monitors input signals from sensors and switches, makes decisions based on programmed logic, and then controls output devices like motors, valves, and relays. PLCs usually work with ladder logic or function block diagrams, which are easy for engineers to understand. They are built to be strong and reliable, even in harsh industrial environments. PLCs have an interesting history. They were first invented in 1968 by Richard Morley for the automotive industry. The goal was to replace complicated relay logic panels with something easier to program and maintain. Over time, PLCs evolved to include advanced features like Ethernet communication, SCADA integration, and even IoT connectivity. Today, modern PLCs are smarter, faster, and more connected than ever before. A PLC has a simple but powerful architecture. It starts with a power supply that provides energy to the system. The heart of the PLC is the CPU, or Central Processing Unit, which runs the logic program. Then we have input and output modules. Inputs read signals from sensors and switches, while outputs send commands to devices like motors and valves. There's also a programming device, which is used to write and load the logic into the PLC. Finally, communication interfaces allow the PLC to connect with other systems like SCADA or HMIs. How does a PLC work? It follows a simple cycle. First, the input scan reads the status of all connected devices like sensors and switches. Next, the program scan runs the user-defined logic to make decisions. Then the output scan updates the actuators, relays, valves, or motors based on that logic. Finally, the PLC handles communication and diagnostics, exchanging data with other systems and checking its health. This cycle repeats continuously, ensuring real-time control. PLCs come in different types based on size and application. The first type is compact or fixed PLC, which has a fixed number of inputs and outputs and is used for small machines, like packaging units. Next is modular PLC, where you can add or remove modules as needed, making it flexible for medium to large systems, such as assembly lines. Then we have rack-mounted PLCs, which are used in big plants and allow multiple modules to be installed in a rack, common in steel or cement plants. Finally, distributed PLCs, which are spread across different locations and connected through a network, perfect for large-scale automation like oil and gas facilities. A PLC is made up of several hardware components. First, we have input modules that read signals from sensors and switches, like a temperature sensor or a push button. Then, output modules send signals to field devices such as pump motors or solenoid valves. The CPU is the brain of the PLC, executing the logic program. Memory stores the program and data for smooth operation. Finally, communication ports allow the PLC to connect with other systems, for example, linking to an HMI or SCADA system for monitoring. These parts work together to make the PLC a complete control solution. PLCs are programmed using languages defined by the IEC 61131-3 standard. There are 5 main types. The most common is ladder diagram, which looks like electrical circuits and is easy for electricians and engineers to understand. For example, ladder logic is often used for motor start-stop control. Then we have function block diagram, which uses blocks for logic. Structured text is similar to high-level programming languages like Pascal. Instruction list is a low-level, text-based language, and sequential function chart is used for step-by-step processes. These languages give flexibility to design control logic for different applications. PLCs don't work alone, they need to communicate with other systems. Common communication protocols include Modbus, Profibus, Ethernet/IP, and Profinet. These allow PLCs to share data with SCADA systems, HMIs, and even other PLCs. Networking makes remote monitoring and control possible, which is very useful in large plants. For example, an operator can check pump status from a control room without going to the field. Think of these protocols as different languages that PLCs use to talk to other devices. PLC and DCS are both control systems, but they serve different purposes. PLCs are mainly used for discrete or machine control, like packaging machines, and they work with high-speed logic in a centralized structure. On the other hand, DCS, or distributed control system, is designed for continuous process control, such as in oil, gas, or chemical plants. DCS uses a distributed structure and is slower but very accurate for analog control. Think of PLC as a sprinter, fast and focused on short tasks, while DCS is like a marathon runner, steady and built for long continuous processes. Let's compare PLC with a traditional local control panel. A PLC system is automated, which means you can easily change the logic using software without rewiring. It also allows real-time monitoring through an HMI and supports data logging for better analysis. On the other hand, a local control panel is manual. Any logic changes require physical rewiring, and it offers limited indication with no data logging. Think of PLC as a smartphone, smart, flexible, and connected, while a local control panel is like an old landline phone, basic and limited. There are several big names in the PLC industry. The most popular is Siemens, widely used in Europe and many global projects. Allen Bradley, from Rockwell Automation, is common in North America. Mitsubishi Electric and Omron are strong players in Asia. Schneider Electric is also a major brand, along with ABB and Beckhoff. Each manufacturer offers different models and features, but all aim to provide reliable automation solutions for industries. PLCs are used in almost every industry today. In water treatment plants, they control pumps and valves to maintain flow and pressure. In cement and steel plants, PLCs manage heavy machinery and production lines. Oil and gas refineries use PLCs for process control and safety systems. Packaging and bottling industries rely on PLCs for speed and accuracy. Even automotive assembly lines use PLCs to coordinate robots and conveyors. Think of PLCs as the silent managers behind every automated process, making sure everything runs smoothly without constant human intervention. Let's look at a simple example of PLC in action, controlling the water level in a tank. Sensors measure the water level and send signals to the PLC. The PLC runs a logic program. If the level is below the low limit, it turns the pump on. If the level goes above the high limit, it turns the pump off. This ensures the tank stays within the desired range. The PLC also sends feedback to the HMI so the operator can monitor the status in real time. Think of it like an automatic water tank system at home, but smarter and industrial grade. Why do industries prefer PLCs? First, they are highly reliable and can run for years without failure. Second, they are easy to reprogram, so changes in process don't require major hardware modifications. PLCs are compact and modular, saving space and allowing flexibility. They also help in energy-efficient operations and provide real-time monitoring and diagnostics. In short, PLCs make automation smarter, safer, and more cost-effective. Think of them as the backbone of modern industrial control. Keeping a PLC system healthy is important. Start by using diagnostic LEDs and software tools to check the status of the PLC. If there's a problem, verify input and output signals to make sure sensors and actuators are working correctly. Always keep a backup of the PLC program so you can restore it if needed. Regular maintenance of the power supply and communication lines is also essential to avoid unexpected failures. Think of it like servicing your car. Regular checks keep everything running smoothly. Here is the key checklist. Check diagnostic LEDs for errors. Verify input and output signals. Inspect wiring and connections for damage. Backup and update PLC programs regularly. Clean PLC modules and remove dust.
Test communication port and network links.
Ensure stable power supply and grounding. Review error logs and alarms in software. Replace faulty modules immediately. Schedule preventive maintenance every 6 to 12 months. Let's quickly summarize what we learned. PLCs are the backbone of modern industrial automation. They provide efficient, flexible, and reliable control for machines and processes. With features like easy programming, real-time monitoring, and strong communication capabilities, PLCs have become an integral part of Industry 4.0. In short, they make automation smarter and industries more productive. Remember, understanding PLCs is a key skill for any engineer working in automation today. Thank you for watching this video. Do subscribe and like for more informative videos.